Hi everybody, so this is going to be a video on how to handle gas law problems when you know 3 of the 4 variables. So the basic equation that relates all gases together is the following equation. PV equals nRT, where P is pressure, V is volume, N is the number of particles, and T is the temperature. R is a constant that is constant for all gases, assuming ideal conditions. So the strategy for these problems is you're going to be asked to find a missing variable, and you're going to be given 3 of the 4 variables, and your job is to try and figure out what that 4th variable is. So the strategy here is to be organized, right? Try to figure out what the pressure is, the volume is, the number of moles, and the temperature. The gas constant R is always going to have the same value. Here I'm going to use the gas constant 0.08206 liter atmospheres per mole Kelvin. So, right, when you are using this equation, you have to make sure that the units match when it comes to pressure, volume, moles, and temperature. And how do you know that the units match? Well, if you take a look at the gas constant, see how the gas constant is in liters here? So liters is going to be your volume. That's the unit you want your volume to be in. If it isn't in that unit, then you have to do a little bit of conversion. ATM is the unit for pressure, mole is the unit for number of particles, and Kelvin is the unit for temperature. So, in these problems, you want to identify what your pressures are, what your volumes, moles, and temperatures are, and then do any conversions necessary to get it to match the gas constant. So let's read this question, right? At what temperature does a 1.0 mole sample of gas need to be at to exert 960 kilopascals of pressure on an 850 milliliter container? And so when you're taking a look at problems like these, it's helpful to keep in mind that there are a bunch of conversions. So, right, if we take a look at the conversion chart here, ATM is our unit for pressure. And if you aren't in units of ATM, you're going to have to do some conversions in order to get it to ATM. In our problem, we started with kilopascals. And so if you take a look at the unit chart, the conversions here, kilopascals to ATM involves dividing your number by 101.325. This is just the conversion factor to get to convert. Okay. There's also liters, that's for volume, moles, that's for number of particles, and Kelvin, that's your temperature. Right? And for each of these, if you're not in that unit, you may be given, mass, in which case you would divide by molar mass. You might be given milliliters, in which case you divide by 1,000. You just got to figure out where you are in this chart and then convert all the way until you get to the end. Okay. So in this problem, we have pressure. So I know that 960 kilopascals is going to be my pressure value. And I know that because kilopascals is a unit of pressure. And also the wording of pressure here implies that the measurement deals with pressure. Milliliters, that's a unit of volume. So my volume is 850 milliliters. And then moles, that deals with the number of particles, 1.0 moles. Finally, temperature, well, we don't know what temperature is. That's actually what we're trying to solve. And so at what temperature implies, well, we don't know the temperature. So if we compare our units to our what we're given, well, our pressure is not an ATM. So we are going to have to do a conversion step to get it to ATM. Our volume is also not in liters, so we're also going to have to do a conversion step to get it to liters. Our moles, they're good. so we don't have to do any conversion there. Our temperature when we solve is going to be in Kelvin. So it doesn't specify what temperature to solve for, so we're just going to leave it in Kelvin. Okay, so let's take a look at our chart, right? So taking a look, to go from kilopascals to ATM, it looks like we have to divide by 101.325. So if we take a look at our pressure value, 960, and divide it by 101.325, we are going to get a ATM value of 9.47 ATM. To go from milliliters to liters, again, if we take a look at our conversion chart, to go from milliliters to liters, it looks like we divide by 1,000. So 850 divided by 1,000 is 0.850 liters. Our mole value, that's good, and our temperature value will be in Kelvin. So, right, PV equals nRT. Plugging in for pressure, volume, and number of moles, as well as the gas constant, we get that 9.47 ATM. So I'm going to actually skip writing the units because I know that my units all match. Okay, so 9.47 ATM times 0.850 liters is equal to 1.0 moles times, let's see, we have 0.08206 liter atmospheres per mole Kelvin times our temperature, which we are trying to find. Okay, so a little bit of algebraic manipulation, right? You'll divide both sides by 1, you'll divide both sides by the gas constant, 0.08206. So 9.47 times 0.850 divided by 1 divided by 0.08206 gets us a temperature value of 98 Kelvin. So again, the strategy for these problems is figure out what your units are, figure out what your variables are, and the values there, convert if necessary to each of those units so that it matches the gas constant, and then plug it in and solve for the missing variable. Take a look at a second question. We got 8.05 grams of chlorine, Cl2, contained at 20 degrees Celsius and 2.05 atmospheres of pressure. What is its volume? So again, PV, nRT. My pressure here, let's see, I got 2.05 ATM, right? So there's my pressure unit. My volume, well, that's actually what we're trying to find, so I don't know what my volume is. Moles, well, we don't have moles here, but we can get moles from the 8.05 grams of chlorine gas. Remember that chlorine gas has a chemical formula of Cl2. R is our gas constant that'll always be given to you, 0.08206 liter atmosphere per mole Kelvin. And finally, the temperature here is 20 degrees Celsius. Okay. Next, let's make sure our units match. ATM, we're good there. Volume will be in liters. So we have to convert grams of chlorine to moles of chlorine. And then we have to convert our temperature, 20 degrees Celsius, to Kelvin. Okay. So let's take a look at our conversion chart. In order to go from grams to moles, we divide by the molar mass, right? So if we take a look at the periodic table, each chlorine is 35.453 grams per mole. So since there are 2 chlorine atoms, the atomic weight here is going to be 70.9 0.906 grams per mole. The conversion chart suggests that we divide our grams by the atomic weight, the molar mass. So we're going to take 8.05 and divide by 70.906. That will get us a value of 0.114 moles of chlorine. For our temperature, so let's take a look at our conversion chart. To go from Celsius to Kelvin, looks like we just add 273.15. So we take 20, add 273.15, and we get 293.1. Now we're ready to use the equation PV equals nRT. So let's plug in our pressure, 2.05 times our volume. Let's see, then our moles, 0.114 times our gas constant, 0.08206 times our Kelvin value, 293.15. Algebra, 0.114 times 0.08206 times 293.15 divided by 2.05 gets us a volume of 1.33. So again, in these problems, you'll want to identify your pressure, volume, number of particles, gas constant, and temperature, and do any necessary conversions before you use the equation PV equals nRT. Third problem, how many moles of gas are in a 1250 milliliter sample at 1857 torr and 80 degrees Fahrenheit? Okay, so if we take a look at our variables, this is our volume, that's our pressure, and that's our temperature. Milliliters is a unit of volume, torr is a unit of pressure, and degrees Fahrenheit is a unit of temperature. So, pressure, volume, number of particles, temperature, and the gas constant. Our gas constant again is 0.08206 liter atmosphere per mole Kelvin. So we got to make sure our units match. Our pressure is 1857 torr, which means that we need to convert to ATM. Our volume is at 1250 milliliters, which means we need to convert this to liters. We are trying to find the number of moles, so that's the number of particles. And then we have 80 degrees Fahrenheit. We have to convert that over to Kelvin. Okay, so if we take a look at our conversion chart, so torr to ATM involves dividing by 760. 1857 divided by 760 gets us 2.44 ATM. Then if we take a look at our conversion chart for milliliters to liters, we divide by 1,000. 1250 divided by 1,000 is 1.250 liters. We don't know the number of moles. The temperature, take a look, is 80 degrees Fahrenheit. So, taking a look at our conversion chart, we'll need to convert Fahrenheit to Celsius and then Celsius to Kelvin. So Fahrenheit to Celsius looks like we're subtracting 32, then dividing by 1.8. So it looks like we have to do a little bit of intermediate math. So 80 minus 32 divided by 1.8 gets us 26.67 degrees Celsius. And then from there, add 273.15. Taking a look at the conversion chart, add that. Gets us 299.82 Kelvin. Again, PV equals nRT. Plugging in our values, 2.44 times 1.250 equals n times 0.08206 times 299.8. Doing a little bit of algebra. 2.44 times 1.250 divided by 0.08206 divided by 299.82 gets us 0.079 moles. Finally, question 4. A 0.55 mole sample of gas is held at 350 Kelvin in a 2-liter vessel. What is its pressure? So pressure is something that we don't know. Volume 2.00 liters. Number of particles 0.55 mole. Temperature 350 Kelvin. Lovely. All of these units are in the right units. So 0.08206 for the gas constant, liter atmosphere per mole Kelvin. We got liter, we got mole, we got Kelvin, so we're good, meaning our answer is going to be in atmospheres. PV equals nRT. So P times 2.00 is equal to 0.55 times 0.08206 times 350. So pressure is equal to, if we do that math, 0.55 times 0.08206 times 350 divided by 2 gets us 7.90 ATM. Hopefully that helps. Take care, everyone.